Hello, everyone, and thank you for coming. Today, we'll be talking about a penetration testing framework for software-defined networks, which is called Delta. And before we begin, let me introduce ourselves briefly. My name is Sung Soo, and this is Chinu, and we have Seung-won, who is sitting in the front row. And we are the graduate students at KAIST and currently working with Professor Seung-won Shin. And he is leading network and system security laboratory at KAIST. We have been working on various SDN security projects, and among them, today we would like to introduce Project Delta. So this is a summary of the contents. So first, we would like to briefly talk about the motivation of Delta, and for better understanding, we described some backgrounds on SDN and OpenFlows and security of SDN. And after that, we introduce our Delta framework in detail and show some attack demonstrations. And lastly, we have the final remarks. So why we need Delta? Although the attention to SDN has been growing as a next-gen networking, the security of SDN, the SDN networks are still prone to security threat. So we need to verify the security of SDN by running the security test. But the problem here is that manually testing each attack is very time-consuming and annoying job. So like the Nessus or Metasploit that targets the traditional networks, we need an SDN-specific pen testing framework. So Delta has been developed. So by using Delta, we can automatically reproduce known attack cases, and also we can find new vulnerabilities by randomizing SDN control flows, such as OpenFlow. So to easily understand Delta, we need some backgrounds on SDN and OpenFlow. So let's have a look at what they are. So in the traditional networks, there are two problems when many companies are scaling up their networks. The first one is that network and security devices are too expensive because it consists of vendor-specific software on top of specialized hardware. And also they are mostly closed platforms, so it is very difficult to add new functionality or protocols to the devices. And also there is a maintenance cost as well. So if there are more devices on the networks, the more complicated to maintain them. So to deal with the increase in network management, you have to spend more money to keep it up and running. So in short, scaling up network is all about money. So they really want to save on money as possible. So to overcome those problems that I mentioned in the previous slide, software-defined networking is proposed. And the key idea of SDN is separation and centralization of control plane. So as you can see here, the network devices that we are familiar with today can be broken down into two different planes. The first one is the control plane, and this is a software components that makes routing decisions and conducts other network functions. And another is a data plane, and this is a simple packet forwarding device. So it just forward or drop the packets from the control plane decisions. But in SDN, they separate the control planes from the devices and then centralize it into the SDN controller. So the SDN controller is connected to all the data planes and communicate with them using SDN protocol known as OpenFlow. Basically, SDN controllers provide the useful network functions such as switch discovery, host discovery, and routing computation, and so on. So whenever you connect those devices to the SDN controller, the controller automatically constructs a global network view, so it is far easier to manage the network devices in SDN. And also, it is possible to flexibly customize the network functions using the open APIs that most of the SDN applications available today expose. So you can easily develop various SDN applications such as DHCP, firewall, and DDoS detector, and so on. So this can be new opportunities because unlike the traditional network, now you have the global network view and innovative network functions in these SDN applications. So you can just deploy it into your SDN so that the SDN applications automatically manage the networks. So for that reason, SDN is known as a programmable network today. And as I mentioned before, SDN controller and the switches communicate with each other using OpenFlow protocol, and it is currently maintained by an Open Networking Foundation, which is an organization dedicated to the standardization of SDN. So OpenFlow is a de facto standard protocol in SDN. And as you can see in this version timeline, The first release was in 2009, and the latest version is 1.5, which was released in 2015. And although the latest version is 1.5, in practice, most of the OpenFlow enabled switch devices support two prevalent OpenFlow versions, 1.0 and 1.3. In OpenFlow 1.0, every OpenFlow message begins with the same header structure, as shown in the top right. And following the header, the body section starts in accordance with each OpenFlow message type, such as packeting or flow mode. So in OpenFlow 1.0, there are 22 message types in total. And in the case of the OpenFlow switch, it consists of a flow table and handles the incoming packets in 3 steps. So first, when a packet arrives at the switch looks up the flow rules in the table by looking up header fields such as import and Ethernet type and IP addresses and so on. So if the packet is matched to a specific flow rule, any actions for that flow rule are performed on the packet. For instance, the switch can forward the packet to the other port or modify the header fields. And after those actions are executed, the switch increases the counters of the flow rule, such as packet counts or byte counts. So those counters can be used to analyze the flow statistics from the controller later. So let's have a look at the basic operation of OpenFlow. And here we have a very simple network topology with 1 switch and 2 hosts. So when connecting to the SDN controller, the switch exchanges the OpenFlow hello messages with the controller first. And after the handshake process is done, in this example, host A tries to send a packet to host B. But since there is no matched flow rule in the table, according to the OpenFlow specification, the switch sends a packet message, including the incoming packet header to the SDN controller. Then, in order to install new flow rule, the controller sends flow mode message to the switch so that the packet can be forwarded to its original destination. So as you can see in this installed flow rule in the table, the matched fields have import, Ethernet type, and destination IP address. So since the packet is matched to this flow rule, it can be forwarded to host B, and the counters of the flow rule increase as well. As I briefly mentioned, in addition to OpenFlow 1.0, OpenFlow 1.3 is widely used as well. So the noticeable differences between them are as follows. And so first of all, there are more 7 message types in OpenFlow 1.3. And this is for supporting multiple controllers, group table, meter table, and so on. So you can find a detailed description about that in OpenFlow 1.3 specification. And so with such a version upgrade, OpenFlow 1.3 enhanced the reliability, scalability, and efficiency of the protocol than OpenFlow 1.0. So as I described in the previous slides, there are many advantages of SDN. So many companies are adopting SDN these days. For instance, the telco companies like Deutsche Telekom, AT&T, and Verizon are building 5G networks and wide area networks using SDN. And also, the major companies like Google and Facebook are using SDN to build their data centers. And not only the industry, but also the military in the US are considering to adopt SDN into their military networks. Because of the military network characteristics, it seems that they prefer the centralized network management with the global network view in SDN. So now question is, what about the security of SDN? Although SDN offers the significant advantages over the traditional networking, the security of SDN has not been sufficiently verified. So we wanted to ask if they are really secure to be deployed at the production level. So first, to simply check out the academic area, we investigated how many papers are related to SDN security have been published in recent years. And as you can see in this graph, the number of those papers has increased every year since 2013. And also, in this Black Hat USA, the briefings and the seminar sessions about the SDN security have been published as well. So we can find out that SDN security has become a real and serious problem, so we need to further analyze it. So here we have a typical SDN architecture, and it can be broken down into 3 layers: control plane, control channel, and data plane. And also each one can be an attack vector as well. So let's check out which vulnerability exists in each layer. So the first one is the control plane, and actually this is the SDN controller. And in SDN, SDN controller can be considered as a brain of network because it knows everything about network and has a full control over it. So it is single point of failure, and therefore any type of DOS attack against SDN controller will immediately make the entire network unavailable. So one possible DOS attack is known as a packet flooding attack, where an attacker can generate a lot of random traffics leading to sending busted SDN packet message to the SDN controller so that the controller can be unavailable. And in the case of the control channel, an attacker can guess the network topology information through the ongoing SDN messages if there is no encryption. But actually, OpenFlow supports TLS and SSL encryption, but that is not mandatory, and in practice, that's rarely used due to its performance impacts. And lastly, if an SDN controller or SDN application is compromised, they can push a lot of flow rule traffics to the OpenFlow switches, causing flow rule flooding attack, which is just the resources on the switch, and so that the performance degradation on the switch can happen. In addition to those other cases that I mentioned in the previous slide, there have been many other cases in each layer, as shown in this SDN vulnerability genome project. So we believe the network operators who are seeking adoption SDN would want to know if various SDN components are vulnerable to those other cases or not. So one possible question is how many SDN vulnerability existing now? And also, if we have the known attack security test scenarios, how to replay each one? Because manually testing each attack in different SDN components is definitely not a simple task. And also, passing all the known security test cases does not necessarily mean that an SDN component is secure, as there may be unknown attacks. So in order to resolve those questions, from now on, I'd like to introduce a security assessment framework for SDN called Delta. And here we have 4 design goals that Delta aims to accomplish. First, it should be highly automated to minimize the human efforts, because as I briefly mentioned, it can be very time-consuming task to manually set up each SDN component and run the security test and verify the test results. And also, Delta should be able to find new vulnerabilities as well. So in our framework, we specifically aim to first test SDN control flows, such as OpenFlow in OpenFlow-based SDN. And third, Delta should support various SDN components. For instance, currently Delta supports 4 open source SDN controllers, including ONOS and OpenLI. And in the case of the switch devices, any OpenFlow-enabled switches can be tested. And lastly, when reproducing known attack cases, Delta should cover as many attack scenarios as possible. For that, we don't need any other testing tools. So let's take a look at how Delta achieve each design goal. So this is how Delta looks like. Delta consists of 1 agent manager and 3 different types of agents: application, channel, and host agent. And the agent manager is communicated with all the agents in the network using a dedicated Delta control channel, shown as red dot line in this slide. So let's have a look at each component in detail. The first one is the agent manager, and it is basically control tower that manages and controls all the agents in the network. So the users would access the agent manager to configure and perform the various security test cases against the target SDN. So, and whenever the test case is done, the agent manager collects each test result from each agent and then makes a decision whether the test case is a success or not. And the application agent is an SDN application running inside a target controller. And it includes various known attack scenarios that could be performed by an SDN application. So we need to develop different SDN application agents against each controller, because each controller provides their own network functions and open APIs. And it has the fudging modules for finding new vulnerabilities. So it can intercept, forge, and change the SDN control messages in the controller. The forging technique used in Delta will be explained in a later slide. And the channel agent is located between the controller and the switch. And similar to the application agent, it also comes with the forging modules that can sniff and modify the ongoing SDN control messages in the between the controller and the channel on the switch. And as a proxy, the channel agent can impose a delay on each SDN control message by capturing and releasing it. And in order to reduce the test running time, it can simulate a simple SDN controller against a target switch under the test and vice versa. And lastly, host agent acts as a normal host participating in the target SDN. So it is capable of generating network traffic to any accessible targets. For instance, the host agent sends a large volume of network traffic to the OpenFlow switch, causing a packet flooding attack that I mentioned before. And it can be used to verify the connectivity to the other host or whether there is a performance degradation on the switch from the traffic latency. So this is how Delta basically works. As I mentioned briefly, Delta provides two operation modes, reproducing known attack cases and finding new vulnerabilities. So the network operator can choose either one of the modes, and when in the case of the reproducing mode, the operator has to select the test cases as well. Then the agent manager instructs each agent to take different actions according to the selected test scenarios. Then when finding new vulnerabilities, the forging modules in each agent randomize the SDN control flows from their location. After the test case is done, the agent manager collects the test result from each agent and analyzes it. Finally, the agent manager tells the network operator if the network has passed the test cases or not. So from this brief workflow, we can see that Delta is a highly automated framework, which is our first design goal. And in order to find new security holes in SDN, Delta randomizes the flow SDN control flows by adopting the black box forging technique. And to more efficiently and systematically randomize it, we first classified the control flows into three different types based on each operations. So the first one is the symmetric control flow, which is the request and response message pair. So if the controller or the switch sends a request message to the other one, the receiver has to send a response message. For instance, there are echo request and response message pair, which is to check if the controller or the switch is alive. And the second one is the asymmetric control flow, which is the unidirectional message, such as packet-in or flow mode that I mentioned several times. So in this case, the receiver does not have to send a response message. And lastly, we have the intra-controller control flows, which is actually OpenFlow-related API call chains between SDN applications and core services provided by the controller. So leveraging those three types of SDN control flows, we derived an operational state diagram of a typical SDN controller, as shown in this picture. So in this diagram, the state labeled R stands for the ready state to receive or send the SDN control messages. And the other states are labeled in accordance with each control message type. So based on this state diagram, the forging modules in each agent take two steps to find new vulnerabilities. So first, each agent identifies the current state of the target controller and then manipulate the flow sequences or the input values of the SDN control flows. So the first step is identifying the current state of the target controller. And here we have the very simple example showing how it works. So first we assume that the current state is in the ready state, and when the controller receives the packet message from the switch, the channel agent in the middle notifies it to the agent manager. So the current state is moved into state A2. And once the controller hands it over to the application agent, the state transition to A3 happens through the application agent. And lastly, after the controller sends a flow mode message to the switch, the current state has become the state A4 by the channel agent. So the point here is that in Delta, the channel agent collaborates with the application agent to identify the current controller state. And next, let's have a look at how Delta randomizes the flow sequences and the input values. So one example SDN operation that involves the symmetric flow sequences would be a handshake process between the controller and the switch. So according to the OpenFlow specifications, this operation should experience total 7 state transition from state R to state S7, as shown in this figure. In the case of the control message types, the handshake process takes from hello message to the set configuration message sequentially. But what if we could manipulate the order of those events? So in this example, we can intentionally send get config response message instead of feature response message to the controller to see what if anything goes wrong. And ultimately, we should try other combinations of those events to discover new vulnerabilities. So in Delta, to automatically carry out such tests in Delta, the channel agent take part. And to first test the asymmetric flow sequences, Delta can randomize the unidirectional messages delivered to the SDN applications. So for instance, when a controller captures a packet message from the switch, the controller propagates the message to the SDN applications that are interested in such type of message in a specific order. For instance, the order of reception is from application A to the application D, but we can manipulate the order inversely so that now the application D can receive the packet message first. So in Delta, the application agent take part of such randomizing asymmetric flow sequences. And randomizing the input values of the SDN control message is pretty simple. So first, the fudging modules in the channel agent can manipulate the contents of the ongoing SDN control messages between the controller and the switch. For instance, when controller sends flow mode message to the switch in order to install new flow rule, the channel agent can modify the command fields of the flow mode message to the undefined value. And then the channel agent should check the response message from the switch as well. And also, the application agent can randomize the contents of the ongoing SDN control messages among passed within multiple number of SDN applications in the target controller, so that the other applications could be in a chaotic state. So from those randomizations, we have found 9 new cases that will be demonstrated in later slides. So Delta can achieve the second design goal, that is finding new attacks. And implementation. Delta is mostly implemented in Java and Python language, and about the lines of codes of each component in Delta. As you can see here, the agent manager take the most part, and the channel agent is second one, and lastly, the host agent is quite simple. And in the case of the application agent, as I mentioned before, it should be differently implemented against each controller. So except for the Ryu agent that is Python-based, each application agent has about 800 lines of code on average. And currently, Delta supports 4 open source SDN controllers: Honest, OpenDaylight, Floodlight, and Ryu controller. And as you can see in the top table, the latest version of each controller can be tested. And Delta supports 2 OpenFlow versions, OpenFlow 1.0 and 1.3. So any OpenFlow enabled switches that are fluent in these versions can be tested. And as you can see in the top bottom table, we have tested PK8, Arista, HP hardware switches, and Open vSwitch. So we can say that Delta is interoperable with diverse SDN components, which is the third design goal. And for the user's convenience, Delta provides the web-based user interface, and it consists of 3 main parts: live test queue, and configuration log pane, and the test case inventory. In the live test queue, each test case is shown with different colors according to its status and result. So first, when the test case comes into the test queue, it's shown with white color, which means that its status queued and result is unknown. And the test case is shown with yellow color during the running status. And after the test case is done, its status has become the completed, and the color is changed to either green or red, depending on its result. And the configuration analog pane, as you can see on the left, we can dynamically set up the target SDN controller, target OpenFlow version, and IP addresses, and so on. And on the right, Delta shows the main log information from the agent manager at runtime. And in the test case inventory, it holds all the available test cases, so the user can push each test case into the live test queue. And here we have three different types of the test cases. So the test set 1 and 2 are kinds of OpenFlow conformance test cases, so that we can test each control message type against the controller or the switch according to their direction. And lastly, we have the advanced security test set, which is related to the SDN controllers architectural weak points exploiting SDN applications. So the number of those test cases that Delta currently provides is about 40. So Delta achieved the last design goal that Delta should cover many attack scenarios. So until now, we have looked at what Delta is and its 4 design goals and its implementation. And from now on, Jinu will show the attack demonstrations.
So we'd like to demonstrate real attacks that we found and share with you some interesting results. First, we have a look at the testbed briefly, and we present 1 known attack and 2 new attacks. For each attack case, we describe a detailed attack scenario and show a demo video, and finally, we have a discussion. For the demonstration, we set up simple test topology with 2 switches and 2 hosts, and all the switches support 2 OpenFlow versions, OpenFlow 1.0 and 1.3, and each one is physically connected to an SDN controller. And in the case of the SDN controllers, we tested ONOS OpenDLI FlowDLI controllers. And for the OpenFlow switches, we tested PICA8, which is one of the hardware switches, and OpenV switch, which is running on the virtual machine. And the agent manager and each agent of Delta are running on each Ubuntu server machine. So the first known attack is packet data forge attack, but before we demonstrate it, we'd like to want to know about an event subscription in SDN controller. In general, SDN controllers have the event subscription list for each SDN message type. So if an SDN application wants to receive the message, the application can register in the subscription list, which is managed in the internal database. And the applications in the subscription list have their own priority. So the higher the priority, the faster the reception of a message. And in this example, the load balance app is ranked as a top priority, so it can receive the packaging message from the controller first. And after processing the message, the load balance app can hand it over to the next application, as you can see here. But what if we can manipulate this subscription list? So here we have an attack strategy that smashes the subscription list. Assuming that a malicious application is installed on an SDN controller, the application can conduct an attack as follows. First, it accesses the internal database and modifies the subscription list so that the malicious application can have a top priority of receiving the messages. So this malicious application can receive the packaging messages from the controller first. And now it modifies the data in packaging message to malformed values, and the manipulated packaging message is delivered to the next application. So when the next one refers the wrong value, it can result in error in the internal of the application. So now let's see how Delta can reproduce this attack in a systematic way. First, the agent manager instructs the app agent to manipulate the subscription list. Then the app agent running on the SDN controller modifies the subscription list so that the app agent can have a top priority of receiving the packaging messages. After this, the agent manager orders the host agent to generate network package, which intentionally makes the OpenFlow switch send a packaging message to the controller. So the app agent receives the packet message as it is the first one in the subscription list. Now the app agent removes the payload of the packet message, so which means that the payload becomes a null value. And the modified packet message is delivered to the next application, which is topology manager in this example. So when the topology manager tries to access the empty payload, it can trigger a null point insertion error in the controller, and this violation makes the controller disconnect the switch or links, and which is one of our criteria that evaluates whether an attack is successful or not. So now let's take a look at the demo video. In this video, on the left, we have Delta WAM UI, and on the top right, we have Floodlight controller, and the bottom right, and the Wireshark is learning, which shows OpenFlow package between the controller and switches. And also, as you can see on the left, we can configure various SDN-related parameters, such as target SDN controller and OpenFlow version. So now in the test case inventory, we can pick the prepared attack cases as well. And this attack case is targeting Floodlight version 1.1, and when we run the attack case, the agent manager automatically executes the target SDN controller and each agent of Delta. And in the log pane, we can see the overall situation in the agent manager and other agents. And please refer to the minimap located on the top left to understand the overall workflow of the attack. And we can see that there are two connected switches on the Floodlight controller. And now the app agent attacks the internal database of the Floodlight to manipulate the subscription list. So here, before the attack, the app agent was the last one in the subscription list. But after the attack, the app agent became the first one to receive the packet messages. So here, the payload of the packet message is removed by the app agent, so the next application refers the empty payload. And as you can see on the Floodlight controller, the switch A is disconnected because of the null point insertion error. And we can also backtrack a reason of the disconnection by looking at the log messages. And here we can figure out that there was a null point insertion error in the Floodlight controller. And finally, since the host agent fails to communicate with the other host, the agent manager decides that this attack is feasible to Floodlight controller. So which means that the attack is successful. So going back to the Delta dashboard, the attack case is marked as a fail. So then why is it possible to Floodlight? The reason is that SDN applications are granted very powerful authority, so which means that the current SDN applications are able to call core services and APIs that provide from the SDN controller without any constraint. So to defend this attack, we suggest that SDN controller should adopt a policy-based access control mechanism like the Android permission system. So the security mode on us is a good example of the permission system for the SDN controller. And the second attack case targets OpenDaylight, which is typically called ODL. And in the case of the ODL, it manages two types of databases. The first one is configuration database, and it can be used for the installation of proactive flow rules that need to be configured before the control channel is established. And the installed rules on the configuration DB are permanently preserved, even if the controller or the channel is closed. On the other hand, the installed flow rules on the operator DB are automatically removed after the control channel is shut down. The important point here is that ODL always refers to the configuration DB when handshaking with the switch. So based on this property, we can design an attack strategy as follows. First, a malicious application injects a malformed flow rule to the configuration DB, and the flow rule has some wrong values that can cause an error. And now, an attacker uses an MI10 proxy to cut the control channel temporarily. So the one of OpenFlow switch will try to reconnect to the controller by sending a handshake message. And the controller will access to the configuration DB to get the predefined flow rules. But here, the controller reads the malformed flow rule, which is installed in the previous step, so this can cause an error in the internal of the controller. So now, again, let's see how this can find out this attack. First, the agent manager orders the app agent to push the malformed flow rule to the configuration DB. And the app agent makes the flow rule including a group action field, which is not supported field in OpenFlow 1.0. Here we assume that the switches are using OpenFlow 1.0 version. After that, the agent manager commands that the channel agent interrupts the control channel in a few seconds. So in this example, the switch A retries to connect to the controller by sending hello messages. But the SDN controller gets a null pointer exception when reading the abnormal value in the configuration DB. So the handshake is continuously failed because the abnormal value is constantly remained in the configuration DB. So we have another demonstration again. And in this demonstration, we have the configuration database on the bottom line. And this attack is effective to OpenAI Oxygen version and will run the attack on VM environment. And the OpenAI GUI will appear at the bottom left. So at the start of the running ODL, the configuration DB is initialized. And before the attack, you can see that there are two connected switches on OpenAI. And now the app agent installs the malformed flow rule to the configuration DB, and the flow rule has a null value in the group action field. So here the channel agent breaks the OpenFlow session for a little moment by sending a TCP reset packet. So after the attack, you can see that the switch A disappeared from the OpenAI web UI. And as shown in the Wireshark, there are a bunch of handshake packets because the handshake is continuously failed. So now, what is the problem of ODL? The first reason is that ODL is not able to handle such an exception when it handshakes with your switch. So which means that even though ODL failed many times, it just repeated the same task without resolving the problem. And another problem is that there is an absence of malformed flow rule management, so it means that ONOS doesn't validate input flow rule. So to defend this attack, we think that ODL should detect the infinite failures of the handshake process, and it needs to locate and resolve the root problem, not just repeating meaningless tasks. And also, ODL should filter on input flow rule when it receives the incompatible field from the application. For example, in the previous attack, the group action field is a feature of OpenFlow 1.3, even though the switches are using OpenFlow 1.0. So lastly, we have an attack case against ONOS. In SDN, the installed flow rule should be same between the controller's flow table and switch's flow table. And this means that there should be suitable synchronization technique in order to accurately synchronize flow rules. So in the case of the ONOS, they use OpenFlow flow statistics message. Let me give you an example. Here, if an ONOS application installs a flow rule to the controller's flow table, the controller reads the flow rule and builds an OpenFlow packet, here which is flow mode packet, and sends it to the switch. So it results in that a flow rule is installed on the switch's flow table. And now the controller periodically collects the flow rules from the switch, and the flow statistics message have information about the installed flow rule on the switch. And this period of time is default 5 seconds in ONOS. And then the controller compares the collected rules with the original one on the controller's flow table, and they check whether they are exactly matched or not. So with this method, the consistency between the switch and controller can be periodically investigated. But the interesting point here is that if ONOS thinks that the consistency is broken, ONOS removes and reinstalls every installed flow rules of the switch. So we can break the consistency by installing a malformed flow rule with an invalid value. So here, the malicious application again installs an invalid flow rule to the controller's flow table, and the flow rule has a big integer value that can be overflowed. Now the controller builds the flow rule and sends it to the switch, but here the injected integer value is overflowed, so it is converted into a different one. And now whenever the controller collects a flow statistics from the switch, it compares the rules with the original one again, but obviously, since they are totally different, ONOS decided to remove all previously placed rules. So finally, again, let's look at how Delta can find out this attack. So we assume that the host agent communicates with the other host, so there are related flow rules on the switches. And now the alternative manager instructs the app agent to make the malformed flow rule. Then the app agent randomly injects an output port number to the controller's flow table. So when the controller builds the open flow packet, the injected output port number is overflowed, so it is changed into the unintended value. But from the controller's view, the installed flow rule on the switch is not matched to the original one on the controller's flow table. So it clears all installed flow rules and tries to reinstall them. But still, they are not same each other due to the overflowed value, so this is infinitely repeated every 5 seconds. So let's take a look at the video clip finally. So this attack is effective to ONOS latest version, and ONOS will appear at the bottom left. And at the start of the ONOS, it installed the default flow rules into the switches, as you can see on the right. And this terminal is connected to the switch PICA8, which is real hardware switch. And here the left table is in the controller's database and right one is in the switches table. Before the attack, they are exactly same. But here, after the attack, you can see that the flow rule on the controller has the big output port number, and it is not same with the actually installed one on the switch A. So ONOS thinks that there was an inconsistency problem when it installed the flow rule from the storage. So it decided to remove all installed flow rules. So as you can see on the Wireshark, there are a bunch of flow mode and flow removed messages, which means that the synchronization continuously failed. So again, why is it possible to ONOS? The first one is that ONOS doesn't conduct a range check against each field carefully. And every 5 seconds, ONOS meaningfully synchronizes flow rules, even though there is a malformed flow rule in the storage. So how do we defend this attack? Obviously, ONOS should check the range of the critical fields in a thorough manner when building a flow rule. And when there is a synchronization failure, ONOS needs to analyze root problem of the malfunction, not just repeating meaningless synchronization. So actually, we've discovered 9 new attacks, as shown in this table, by using Delta. But we demonstrate 2 of them due to the time constraint, and that is malformed flow rule generation and infinite flow rule synchronization. So in conclusion, we all know that SDN is known as a next generation networking because it has significant benefits than traditional one. But still, there are a lot of vulnerabilities, so we need to improve the security of SDN. So with the help of Delta, we can systematically conduct pen testing against the entire SDN architecture. And the forging techniques of Delta allow us to find new vulnerabilities. And our tool is now available as an open source project, so please visit our GitHub and join us. Thank you very much for your listening, and any questions?